this is the kind of problem where I know kind of like exactly what to do. This is 2909 minimum sum of mountain triplets number 2. Okay, let's go ahead and get right into it then. All right, so you were given a zero indexed array nums of integers. Sounds pretty simple. A triplet of indices I, j, k is a mountain if I is less than j, less than k. Okay, so you choose an I somewhere later down the array. You choose a j somewhere later down the array. You choose a k. Nums of I is less than j, and nums of k is less than nums of j. So what does that really mean? Well, you have elements like, 3, 7, 2, for example. Now, this is a mountain triplet. A mountain, if, this is your I here, and this is your j here, and this is your k here. And all it's really saying is, well, this 7 is greater than this 2, and this 7 is greater than this 3. And this is a mountain array, because if you think about this in terms of it being like a mountain, right? 1, 2, 3 units up, 1, 2, 3, 4, 5, 6, 7 units up, 1, 2 units up. This creates a mountain, right? If you look at this, it goes up and it goes down. I don't know if you've ever seen a mountain in your life. Probably. They're found all over nature, right? This is what they look like. So this is a mountain array because, there's some peak, right? And then there's some lower point and some lower point on the left, some lower point on the right, right? Now notice that doesn't necessarily have to be the same point, right? One thing that's kind of tricky about the way that a mountain is defined here is, well, technically you could have, something like this, right? Because we're just specifying what our I and j are, right? So we just look at I. So it's not really like the most clear definition of a mountain, right? Because you wouldn't say that this is like a normal mountain, right? Because it goes up and then it goes down and it goes back up. But we just need to find 3 indices, I, j, k, where nums of I, which is 3, is less than nums of j, which is 7, and nums of k, which is 2, is less than nums of j, which is 7. Okay. But notice that it's not like a conventional thing we think about where it like always is going up and it's always going down. Because technically we could have elements in between I and j and k where it's greater than or less than or whatever. All right, so that's just something to think about. All right, so we're going to return the minimum possible sum of a mountain triplet. So we're trying to find the smallest mountain. All right, so we want the smallest mountain, right? So we want the smallest sum of nums of I plus nums of j plus nums of k. And that just means that we want the smallest, since we want the smallest sum, right? The sum of its parts, individual. So we want the smallest nums of I, the smallest nums of j, and the smallest nums of k, right? So, the point I'm trying to make here with this is pretty obvious, right? If you're trying to find the smallest mountain, minimum possible sum of a mountain triplet, well, then all the values of triplets will be as small as possible. So we're just trying to minimize, nums of I, nums of j, nums of k, okay? Example 1, just to be completely transparent, I've already solved this problem. This one's not that interesting, right? Because the smallest triplet, there's only one mountain in here, right? There's 5 as the peak, and then 1 and 3, right? You can't choose 8 because there's nothing smaller to the left. You can't choose 6 because there's nothing smaller to the left. You can't choose 1 as the peak, right? You can't choose 8 as the peak or 6 as the peak or 1 as the peak because there's nothing smaller to the left. I can choose 5 as a peak because 1 is smaller to the left and 3 is smaller to the right, right? And they're right next to each other. Let's look at this example because it's a little more involved, and I think it'll be a little bit better at kind of revealing something about the solution. All right, so let's do an example here. Let's just separate this area here out. All right. So we have nums equals 5, 4, 8, 7, 10. 5, 4, 8, 7, 10, and 2. All right, now I'm I'm actually going to draw this as kind of like a mountain because maybe that'll, it'll make a better screenshot and hopefully it reveals something about what this solution is supposed to look like. All right. So we got 5 units up, 4 units up, 8 units up, 7 units up, 10 units up, 2 units up. And then let's actually draw those mountains. All right. So this is 5 units up, right? So 1, 2, 3, 4, 5. It's like units of dirt. 1, 2, 3, 4. And then 8 is 1, 2, 3, 4, 5, 6, 7, 8. And I did not create enough space. I was worried that would be an issue. And this is 7. 1, 2, 3, 4, 5, 6, 7. And this is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is 2. All right. Now, again, the mountain doesn't have to be exact. Now, it's saying our answer is 1, 3, and 5. Okay. So this is saying that our I is here at 1, 0, 0, 1, 2, 3. Right. So the index that we're looking at, our 5 is here. Right. Because when we sum these up, we get nums of I plus nums of j plus nums of k. Ooh, my writing is really bad right now. Which is 4 plus 7 plus 2 is 13. And that's why you return 13. Okay. Now, the mountain that we're looking at here, right, is, this 4, this 7, and this 2. And that looks something like this, right? Now, again, we're kind of crossing through to things that are increasing. So it's not like the most standard way of thinking about a mountain, but we have something on the left that's smaller and something on the right that's smaller. Right now we're trying to find the minimum, right? Which makes sense why we kind of have like the 3 minimum elements in here, right? You can't always do that because maybe the way it's oriented, you can't get all the minimums together, right? But you're trying to find minimum points, right? Whatever points you pick, it should always be minimum, okay? Now, how are we going to solve this then, right? The n cubed solution would be to look at all pairs, right? Look at all n cubed pairs, right? Look at all i's, look at all j's, look at all k's, and then sum them up. Figure out if they meet the conditions, right? If they are a mountain, right? Nums of i's less than nums of j, nums of k's less than nums of j. But that would be too slow because we're looking at a constraint 10 to the 5. So our solution should be, somewhere in the realm of O of n to O of, I'm just like making up notation on the spot here, so I apologize for. Right now, it's not saying that this is the optimal solution, right? But something within this range from O of n to O of n log n, that will meet 10 to the 5 condition, right? There's always good indications about what will pass, right? What the upper end is, right? The slowest solution would be. And if it's 10 to the 5, right? Because Leetcode can handle about 10 to the 6 operations before it gives you a time limit exceeded. So this 10 to the 5 means that the upper end, technically there could be a faster solution. It could be a constant solution. I mean, there isn't in this one. I mean, how would that work? But, this gives you an upper end, right? The upper end, right? The slowest our problem can be in order to pass is somewhere in n to n log n space. Okay. And that's what this indicates. But that doesn't mean it isn't faster. It could be faster. We just know that this is the upper limit. All right. So I guess one thing to think about here, right, is, well, when we go through, right, we're always trying to keep track of the smallest things we can use, right? We always want to keep track of what is the smallest element I can get away with here that'll keep me in line. And what I mean by that is, let's look at this problem again, right? And you notice that we're trying to get small things, right? We're trying to constantly look at it and say, oh, I want a small hill. I want small mounds, right? I want small areas to add up so that I always get the smallest sum because I'm trying to minimize the sum here, right? So if I'm trying to do that, something I should think about here is, well, like, as I go through, I should keep track of what the smallest mound is, right? The smallest piece of land is, so that later I can consider it when I'm trying to find this hill array, right? When I go through here, I'll just go through from the left, right? I'll create this little guy here. Let's create this little Voyager, right? This little Voyager, that's us. And I'm just trying to keep track of, what's the smallest thing I've seen so far on the left, right? Because maybe later I can use this as the hill, right? As I'm walking through, I'm thinking, I need to have a small element on my left to connect to. So maybe I should keep track of the small elements on my left. That way, when I get to the top of a peak, I think, what's the smallest element I can connect this peak to, right? When I'm here, when I'm where, right? When I'm on this element, I want to say, I'm at the top of the mountain here, right? I'm at the top of the mountain, and who can I connect to on my left? Who would be the smallest person on my left to be the smallest element that would make this a hill, right? Who's going to be my I element? Who's going to be my K element on the right? So maybe I'll keep track of that information, right? I should keep track of who's the smallest on the left and who's the smallest on the right. That way I know who to connect to. So I start here and I say, oh, the smallest thing I've seen so far is 5, right? And then I go down, I'm like, oh, look at me. I'm at 4 now. That actually means that the smallest thing to the left in the future will be 4, because they can connect to 4. And then I go up at 8 and I say, ooh, 8, that's actually higher. Later down the line, when I want to connect to something to the left, I might as well connect to that 4 that I already saw, not this 8, because that 4 value is going to provide better information. So I'm going to keep this at 4. And then I go down to 7. I say, oh, this 7's good. But you know what? That 4 that I saw before is actually still better, right? Because what I'm doing here is I'm going through and I'm saying, when I create a peak, there's got to be something to the left that I connect to. So I might as well keep track of all the things I've seen to my left and the smallest one, so I know who's the best for that person to connect to at this point. Then when I go to this 10, I'm like, that 4 is definitely better. And I guess technically, when I go to this 2, I'll say, oh, you know what? This 2 would be the best thing to connect to from the left. So that's for the left side, right? For any peak, I got to think of the thing to the left that's the minimum that I can connect to, because I'm trying to make the smallest nums of I, nums of j, nums of k. So this will give me, at any index, what's the smallest thing to my left that I can connect to, and what is its value, right? What's the smallest I value I can use to the left? But I should also do the same thing for the right, right? So then I'll go right. I'll say, okay, the smallest thing I connect to here is 2. Right, when I get here, I say, oh, at this peak, this is way bigger. So anybody in the future, they're not going to want to connect to this. I've seen something small already, and that's that 2. Then I move this guy over again. And I say, oh, this 7 is good, but there's a 2 that's smaller before. Then I move them up. This 2 is smaller. And that's just going to happen for the whole way, right? I go through the whole thing. The 2 is always going to be the smallest value to my left. Right? So now that means at any index that I'm at, right? I have information about what's smallest to my left and smallest to my right. So when I'm at this value, I don't need to actually know what these values are at other points, just that they exist. Right? All I know at this point, I know there's a hill, but I don't really know what it looks like. Right? There's a system over here. And there's a system over here. And what I know at is at this point, the smallest thing to my left is a 4. I know that to my left, there's a 4. And to my right, there's a 2. Right? That's what I know at this point. Okay? Because I can just look at this and say, okay, my smallest to my left is 4, and my smallest to my right is 2. I don't need to know what all the values are anymore. I just know at this point, am I going to be a peak? Well, I'm an 8, right? So my value's 8, and I have a small value to my left that's a 4, and I have a small value to my right that's a 2. So that means I can create a peak here. I don't know which I this corresponds to, right? I just know that to my left there's a 4, and to my right there's a 2. So that's a 4 plus 8 plus 2 kind of situation, right? And that would be the same thing for this one here. If I was dealing with this next index, kind of running out of space here. I'm not going to do it, but if it was the same thing, right? The idea being if if I did it at the 7, right, at the 7, I would know that, okay, at my 7, I have the smallest to my left is a 4, and my smallest to my right is a 2, right? So at this thing, what you're really doing is you're taking your own value, you're adding it to the smallest left value, and you're adding it to, oh, that makes purple, the smallest right value. Let's make sure that's all colored right. Because when you mix colors, you get different colors. Isn't that magical? Right. So you just add those together, and you would just do that for each one. Right? So basically what we do is we log, like, what's the smallest thing to the left? What could be the smallest nums of I to my left? All right, what could be the smallest nums of I to my right? And then you just go through and figure out, okay, can this be a peak? Well, what's the smallest thing to the left that I can connect to? What's the smallest thing to the right that I connect to? And I do that for each possible peak, and then I just return the smallest one. So that is how this is going to work. So basically, in summary, what we did here is we said, well, you know, we want to find the smallest mountain. The mountain can look like anything. I just have something to my left, something to my right, and this peak, right? If I want the smallest sum, that just means I want the smallest of everything, right? I want the smallest nums of I, the smallest nums of j, and the smallest nums of k. So what I should do is just keep track of what the smallest nums of I are to my left and the smallest nums of k are to my right. And then at each peak, just say at this peak, get the smallest nums of I to my left and the smallest nums of I to my right, and sum that and just return the minimum one. So consider each peak, get the thing from the left and the thing from right, and that will run in O of n time, right? Because it'll take n time to get the left array, n time to get the right array, and then m time to look at each peak. Okay? So we look at each peak. We just look at each peak. All right, and this would be a prefix sum solution, right? Because we just prefix sum on the left. It's not really summing, right? But it's a prefix idea where you get the prefix of everything and the suffix of everything, right? So I get the prefix on the left and the prefix on the right. Sometimes they call it prefix sums because it's the general case where you sum things, but it's the idea of, you know, finding the longest prefix and finding the longest suffix, okay? So I'll just call that prefix suffix. All right. So let's go ahead and code this. So we have our left array. Now I'm going to make them default dicts to make our life easier. All right. So left equals default dict. And then we'll just set the minimum value to infinity because that's going to get replaced with whatever value is actually in the array. All right. Now let's take our little traveler, right? And let's find the smallest ith value and the smallest kth value for each value. So we'll look at all I in range length of nums. And then we'll just say, okay, the smallest value here is just the minimum of whatever the smallest value was before, because maybe before I saw a smaller value or the current value that I'm looking at, right? So that's all you're doing here, right? I'm saying, okay, the smallest value right, L of I equals the min of whatever I thought the smallest value was and the current value. Right? So what this basically means is L of I, right, L of I for any value, I'll just say here, right, is whatever I thought the smallest value was before and not nums I minus 1, the current value of I. Right? So either I saw something smaller, either I saw something smaller before or I see something smaller now. So either the thing I saw before is smaller or I'm looking at something that's smaller now. Right, so this would be the thing I'm looking at now. And that would be the answer, right? So for this answer, right, it's 4 because the thing I saw before is smaller than what I'm looking at now.